Hello grade 10s and welcome to this video on resistors in series. My name is Natasha Barton and I will be taking you through this section. Now this is going to be a pretty lengthy video because we will be performing some calculations in it to make sure that you understand everything. So please be sure to pause if you start to get tired and to return to the video when you feel refreshed. Now over here we have an electric circuit and this circuit is drawn in the way that you should be able to sketch electric circuits. We have a battery, and I'm now referring to this as a battery because it is made up of 3 cells that are connected in series. There is a voltmeter connected across the battery, and this voltmeter is measuring the terminal potential difference, or we can just say the potential difference of this battery. I'm using the term terminal potential difference because there's no open switch in the circuit. The circuit is therefore closed and electrons can flow. And they say that the potential difference measured on or across this battery is 10 volts. Okay, it's written very small, but it's 10 volts. Then we can see there are 2 ammeters connected in the circuit. They are connected in series to the battery. When I say they're in series to the battery, I mean the same current that flows through the battery flows through them. We then have 3 resistors, resistor 1, resistor 2, and resistor 3. Resistor 1 has a resistance of 2 ohms, resistor 2 has a resistance of 3 ohms, and resistor 3 has a resistance of 4 ohms. Across each one of these resistors is a voltmeter, and each of these voltmeters is connected in parallel across the different resistors. Remember, we always measure potential difference in parallel. Now we need to explore the relationships between potential difference, resistance, and current in a series circuit. Let's start off with how we calculate the total resistance in a series circuit. We say that when we have a series circuit, then the total resistance, which we can refer to as RS, where the S stands for series, is equal to the resistance of resistor 1 plus the resistance of resistor 2 plus the resistance of resistor 3. Using this formula, we can calculate the total resistance of the given circuit. And of course, when we add 2, 3, and 4, we end up with a total resistance of 9 ohms. Now, what would happen if we added more resistors in series to these current resistors, so R1, R2, and R3? If we added another resistor in series to these resistors, what do you think would happen to the total resistance? Well, we would be adding another number to these numbers, and therefore we can say the more resistors you add in series, the larger the resistance, the total resistance is going to be. Now comes a very important relationship, the relationship between current or of current in a series circuit. We start off by saying that current in a circuit, a series circuit, is constant. What we mean by that, grade 10s, is that if we look at the given circuit, positive charge, because we're referring to conventional current, is going to flow out the positive end of the battery around this way, through resistor 1, 2, 3, through ammeter 2, back to the other side, and through the battery. Okay, so it's the same current flowing everywhere in the circuit. Notice that the thickness of this colorful line that I've drawn has not changed anywhere in the circuit, implying, grade 10s, that the total current in the circuit is constant. Therefore, we know the current through this ammeter is going to equal to the current through this ammeter, and that is going to equal to the total current that flows through the battery. That is described by this. I1, the current measured through ammeter 1, is equal to I2, the current measured by ammeter 2, which is equal to IT, the current that flows through the battery. We say over here that if we would like to measure or calculate total current in a series circuit, we can divide the total potential difference offered by the battery by the total resistance. So let's go and do this for the given circuit. We're going to say the total current, which we're interested in, which is the current that A1 and A2 are measuring, is equal to VT, the total potential difference, divided by RS, where RS refers to the total resistance for our series circuit. We're going to substitute in the values. We have 10 divided by 9. When we put this into our calculators and round off the answer, we get 1,11 amperes. We normally round off to 2 decimal places, but only at the end of the question. Only when we answer the question, not for any calculations that we do in between. Alright, so at this point, we know current is constant, and this is a relationship that we must always remember. What we are saying, and we can write this out as well, is that the current measured through ammeter 1 is equal to the current measured by ammeter 2, which is equal to the total current, and therefore equal to 1,11 amperes. No matter where we are in the circuit, the current is constant. Now comes potential difference, and this relationship is very, very, very important. We say potential difference in a series circuit is divided. What that means is the potential difference that the battery offers is not going to be equal to the potential difference across resistor 1, 2, and 3. They're not necessarily going to be equal to each other. If there's only one resistor in the circuit, then it will be equal. But if we have more than one resistor, it's not going to be equal. What is going to happen over here, grade 10s, is that the potential difference that the battery has to offer is going to be split between the 3 resistors. Okay, and it's going to be split such that the bigger resistor is going to have the largest potential difference measured across it. That's what's going to happen here. If they were all exactly the same, then it would split 3 ways. But in this case, the resistor with the largest resistor will have the highest potential difference measured across it. What I like to say is the battery is behaving like a mom, a mother, okay? And when you look at different children, we tend to find that the child that is the eldest eats the most, okay? So I want you to remember this. Based on that, the resistor with the largest resistance is going to have the highest potential difference measured across it. And the one with the smallest resistance is going to have the lowest potential difference measured across it. Think about it as the baby eating a lot less than the teenager, if that's going to help you. So going back down here, I've written the largest potential difference is measured across the biggest resistor. Now comes the tricky part. Sometimes you're going to be required to calculate the potential difference across different resistors. Let's say that I ask you to calculate the potential difference across resistor number 1. To do so, you're going to take the resistance of resistor 1 divided by the total resistance in the series circuit, and then you're going to multiply it by the total potential difference that is being offered by the battery. Let's go and do this calculation to make more sense of it. This formula that was written down is not going to be provided to you in your tests or exams. You're going to have to learn it off by heart if you're going to use it. So the potential difference across resistor 1 is equal to the resistance of resistor 1 divided by the total resistance of the circuit multiplied by the total potential difference. So this is going to equal to 2 ohms divided by the 9 ohms, which we've already calculated, multiplied by the 10 volts. This is the total potential difference that the battery has to offer. And when we put this into our calculators, we find that the potential difference is 2,22 volts. The potential difference that is measured by V1 across resistor number 1 is equal to 2,22 volts. And it's always easy or best to write these values onto the circuit that's been, or the sketch that has been provided to you of the circuit, that you always have to remember what information you have available. Now let's try and perform the same calculation to determine the potential difference across resistor number 2. So we're going to say the potential difference across resistor 2 is equal to the resistance of resistor 2 divided by the total resistance. We're actually using a ratio, okay? We're using a ratio over here, multiplied by VT. That is going to equal to the resistance of resistor 2, is 3. The total resistance is still 9, which we calculated in the beginning, multiplied by 10. In the end, the answer that we obtain is 3,33 volts. That is the potential difference across resistor 2, and we can go fill that in, 3,33 volts. Now let's try and calculate the potential difference across resistor number 3. That is going to be the resistance of resistor 3 divided by the total resistance in the series circuit, multiplied by the total potential difference offered by the battery. That is going to be 4 divided by 9 times 10. The answer that we obtain over here is 4,44 volts, and we can go and fill that in, 4,44 volts. As you can clearly see, the battery is making sure that the resistor with the largest resistance obtains the highest potential difference, while the resistor with the least resistance has the smaller potential difference measured across it. Now, there's a very important relationship between the potential differences that we measured. We say 2,22 plus 3,33 plus 4,44. We end up with an answer of 9,99, which is approximately equal to 10. The only reason it does not equal 10 is because we rounded off when we wrote down these answers. Now 10 volts, where on your sketch did you see 10 volts? Over here. As you can clearly see, the total potential difference has been divided. Now over here you can see I've indicated that with this formula or this equation, V1 plus V2 plus V3 is equal to V total. And again, I'd like to emphasize that V1 measured across resistor 1 is smaller than V2, which is smaller than V3. This is only the case for this specific circuit because the resistance of resistor 1 is smaller than the resistance of resistor 2, which is smaller than the resistance of resistor 3. And this brings us to the end of this video on resistors connected in series. In the next video, we're going to take a look at resistors connected in parallel.